It was late afternoon on March 27, 1964, when the ground in south-central Alaska began to shake as it never had before in North America, and never has since. For more than 4 minutes, centuries of accumulated compression were suddenly released. The magnitude 9.2 earthquake caused part of the Alaskan coast to lurch forward more than 20 meters. The resulting landslides and mudslides devastated towns and cities. In some areas, unstable land began to behave like water, causing buildings and roads and pipelines to sink into the ground, and dozens of tsunamis, the largest of which topped out at 67 meters high, caused catastrophic damage along the bays and inlets of the coast. More than 125 people died in the Good Friday earthquake, which was felt over an area of about 1.3 million square kilometers, and it released more energy than the combined power of every North American quake since. It's been 50 years since North America's largest recorded quake, and its legacy remains enormous, because it was this natural disaster that ushered in the modern age of earthquake science. Much of what we know today about earthquakes can be traced to work conducted by a handful of geologists in the months and years that followed, and they all started with the same question: how did this happen? To understand what caused the Great Alaskan Earthquake, and really the majority of all earthquakes, we have to start with plate tectonics. Take a look at a map of earthquake activity today, and you'll find that most of the seismic events all over the world take place along the edge of oceanic and continental plates. There are 7 of them, all told, that together make up the Earth's lithosphere, the outermost shell of the planet where you find the crust and the upper mantle. These plates are constantly moving, and they interact with each other in lots of different ways. They can move apart from each other, creating a space known as a divergent plate boundary. When this happens, magma, the molten rock beneath the surface, usually seeps up to fill the crack and form new crust along the boundary. Plates can also push up against each other, creating what's called a convergent plate boundary. Tectonic plates move slowly, just a few centimeters a year, but over millions of years these collisions can create whole new mountain ranges as one plate is pushed up and the other sinks below the surface. Finally, tectonic plates can slide slowly alongside each other, creating what we call a transform boundary. You won't generally find any mountain ranges or lava along these boundaries, but you will find the makings for an active earthquake zone. All of these interactions seem pretty obvious to us today, but not so much just a half a century ago. The theory of plate tectonics had actually been proposed a full 50 years before the '64 quake by German meteorologist Alfred Wegener. But the idea that the Earth's surface floated around in pieces was ridiculed at the time, and Wegener's career was all but ruined. But in the decades that followed, new generations of geologists began discovering things like huge rifts on the ocean floor, which turned out to be the boundaries of Wegener's plates. Even so, by the early 1960s, some scientists saw new crust forming in the middle of the oceans, those divergent plate boundaries, as evidence that the planet was actually growing larger each year. That was the only way they could think of to explain where the other end of the plate had gone. That Alaska quake changed all that. At first, early in the quake's aftermath, some geologists tried to explain the disaster by theorizing that massive plates had just rotated past one another counterclockwise. But a handful of USGS scientists, led by George Plafker, knew that something else had happened, something we'd never studied before. Plafker and his team went to Alaska to study the land, and what they found was weird. In some areas, forests had been submerged under salt water, but in others, rocks with barnacles on them were standing on dry land. The land hadn't moved from side to side, it had moved up. We know it today as a megathrust earthquake, when one plate slowly slides beneath another in a process known as subduction. When the forces build up between these overlapping plates and one of them slips, the result is enough energy to move an entire coastline. Once Plafker and his team figured out what was going on, they realized that the Earth wasn't somehow growing in circumference like some geologists thought. Instead, the plates were recycling themselves in these subduction zones. As one plate slipped under another, it was forced down into the magma where it returned to a molten state. It turned out that the 2 plates involved in the Alaska quake, the Pacific and the North American plates, were the world's largest, making up about 1/3 of the world's surface. And of course, they're still colliding at a rate of about 5.8 centimeters per year, with the lighter North American plate being pushed upward. Today we know that all of the earthquakes with a recorded magnitude of 9.0 or higher, and there have been 6 of them since 1900, have been the result of one of these megathrust quakes. But thankfully, most earthquakes are not megathrusts. The majority occur along those transform boundaries where plates slowly slide past each other. It's this movement that will eventually cause Los Angeles, which is situated on the Pacific plate, to slide right past San Francisco, which sits on the North American plate. That will at least make commuting easier. Of course, this part of the Pacific plate moves about 50 millimeters to the northwest each year, so that'll take a while. And while earthquakes usually occur where tectonic plates meet, they can also happen far from their edges, because plate boundaries are just one type of fault, or fracture in the crust. Faults can form just about anywhere on a plate, as the result of a plate jostling around and bumping into other ones, or sometimes helped along by things like local volcanic activity. No matter what their origin, the constant buildup and release of energy in these faults are what cause earthquakes far from plates' boundaries. So-called normal faults, for example, form where the crust is being pulled apart and the ground above the fault zone drops. One of the largest normal faults in the US is the 240-kilometer-long Wasatch Fault, which extends through Idaho and Utah. As the North American plate moves to the southwest, it stretches, and this area of crust pulls it apart, forming the normal fault. Reverse faults, meanwhile, occur when the opposite occurs and pieces of crust are being compressed together, so the ground above the fault zone is being pushed up. These kind of faults are the Earth's great mountain builders. The Sierra Nevada, the Rocky Mountains, even the Himalaya are all the result of reverse fault dynamics, and it's also the type of fault that caused that megathrust in Alaska. Then we have strike-slip faults, where pieces of the Earth rub against each other sideways. California's San Andreas Fault is probably the most well-known of this kind in North America, while most of the earthquake activity in southwestern Europe is the work of Turkey's Anatolian faults. Like many other aspects of Earth science, we're still trying to understand all of the forces that cause earthquakes. And while the Alaskan quake ushered in a new era of knowledge in terms of how the Earth is pieced together, scientists are still trying to get a handle on questions like how different temperatures within the Earth affect seismic activity. And then there's the big question of whether and how we can predict them. It'd be nice if we could just monitor tectonic plates and send out warnings when a quake is imminent, but those plates are usually about 100 kilometers thick, and the process that occurs before an earthquake is subtle and pretty much impossible to observe. But maybe the most lasting legacy of the 1964 earthquake is all of the scientific institutions that now exist to study and monitor the activity of the Earth. The U.S. Geological Survey's Earthquake Hazards Program, the Tsunami Warning Center, and the Advanced National Seismic System, which monitors seismic activity around the clock, were all created in the wake of the Alaska quake to get a grasp on all the science that's going on right beneath our feet. And there's no shortage of data for them to study. There are more than 500,000 detectable earthquakes around the world each year, 100,000 of which can be felt by humans, 100 of which cause damage. The more we learn, the better scientists will become at predicting when and where earthquakes may strike. Thanks for watching the SciShow Infusion. I hope you learned something, but mostly I hope that our Subbable subscribers learned something, because they are the reason that we can make this show. To learn how you can support us in exploring the world, just go to subbable.com/SciShow to learn more. And be sure to check out our new channel, SciShow Space, where you can learn about other kinds of planetary science along with this week in space news. And as always, don't forget to go to youtube.com/SciShow and subscribe.